Welcome back, students. In this video, we are going to look at epoxides. Let's begin by looking at how epoxides are created. Remember that epoxides are a three-membered ring with an oxygen. So this part over here, this is the epoxide functional group. We've already seen how epoxides are created in a prior chapter where we started with an alkene and we added a peroxy acid. Here is the formula for a general peroxy acid. If we were to draw this out, it would look like this. Your favorite peroxy acid is something called MCPBA. So you might just see MCPBA written instead of the general formula for the peroxy acid. Now, the most common point of confusion right here is when people see MCPBA, they think, whoa, but that created the trans diol. Oh, no, it didn't. MCPBA itself alone created the epoxide. And then what you did was you added acid in a separate step that then opened up that epoxide ring to create the trans diol. So take those two ideas and separate them in your brain. This is what I'm talking about. MCPBA made this epoxide, and then this epoxide, also called an oxirane, is then opened with an acid catalyst. So what will occur is your electrons on the oxygen of your epoxide are going to come over and they're going to pull off a proton. When they do this, now you have a protonated oxygen here. So your water, which is a weaker nucleophile, has the ability to come in and attack from the opposite side. Now, in actuality, this epoxide is not trigonal planar, right? So this is maybe wedged, and this one is wedged, which makes this one wedge, and this one wedge. So when the water attacks, it attacks from the back side. And when it attacks from the back side, that's why you got that trans addition or that anti-addition. So your water came in, it attacked from the opposite side. Now you get bound water, which is called the oxonium ion. And you have your OH here. Now you don't want two protons on this oxygen, but guess what? This is acid catalyzed, which means we have to recreate our catalyst at the end. The way to do that is to say, hey, you know what? When I have water, I actually have a lot of water. So your water molecule is going to come in, pull off this proton, put another pair of electrons on that oxygen, and you will get your trans diol here. Right, so you'll get anti-addition of the two OHs across the pi bond when you start with step 1, MCPBA, and step 2, the acid catalyst. Don't forget about enantiomers here. You could also form the enantiomer of this compound and end up with that racemic mixture. Now let's talk about what would happen if we changed that catalyst. If we have a base catalyst instead of an acid catalyst, it changes a little bit. First, what we're going to see is that our base is strong enough to just attack right away. Again, the same idea here, your epoxide is not planar. You have actually either the epoxide, that oxygen being above the plane of the ring or below the plane of the ring. Here I'm just drawing above the plane of the ring. This is kind of ugly. Let's make that look nicer. Now your base is going to come in and attack. So your base is going to come in and attack the back side, just like how we saw the water attacking the back side. And what will happen is now we'll end up with an O- and an OH. So in a separate step, we need to add some water. We need to add water so that we can have this O- become protonated. And we end up with OH here and an OH here. Remember that you can also attack the other carbon, right? There's equal probability of attacking this carbon that I highlighted in yellow versus this carbon that I highlighted in blue, which means that we can end up with our mixture of enantiomers. Okay, but what happens if you don't have a nice, cute epoxide that's perfectly symmetrical? What happens then? Well, if your epoxide is asymmetrical, then we have to consider some regiochemistry. And the regiochemistry changes based upon if we are talking about using a base catalyzed ring opening or an acid catalyzed ring opening. If we have a base catalyzed ring opening, which is what we're seeing in this first example, where this is my base that I'm highlighting in yellow, your base has an oxygen that's negative and has a lot of electron density around it. What that means is it's difficult for the base to come in and attack this carbon. There's too much there. It's too sterically hindered. So what will happen instead is your base will come around and attack this carbon. So when your epoxide is asymmetrical, and notice how I have this methyl group here that's making my epoxide asymmetrical, what we're going to find is our final product is going to have your OR group, so whatever your base / nucleophile is here, is going to come in and attack from the opposite side. So if we saw wedge here, we're going to see dashed here, and your nucleophile goes to the less substituted side. Instead of starting with something that is a base and thus base catalyzed, we're going to start with something that is neutral and has an acid catalyst. In this case, the regiochemistry changes. What that means is instead of us getting the OR group at the less substituted side, now our OR group is going to add to the more substituted side. So why is this happening? I'm going to draw an intermediate step and show you. So this is not the final product, but it's what happens after that initial protonation. So once you protonate the epoxide, and then the epoxide becomes more readily able to once you protonate the epoxide, then the weaker nucleophile can come in and attack. Now, in order for this to occur, the carbon of the epoxide ring, so the one I'm highlighting in blue or the one I'm highlighting in yellow, has to let go of a bond a little bit. It has to let go of that CO bond and start creating a partial positive. Well, the carbon in blue is better able to create or take on that extra partial positive or a lack of electrons because there's more carbon groups attached to it. So this side ends up developing a greater partial positive charge, which in the grand scheme of the overall reaction ends up with us seeing that your OR group adds to the more substituted side. Because your OR group is adding from the more substituted side and also from behind, what we find is the directionality of this methyl group that was already attached changes. So that comes out as a wedge. Your OR group adds from the back side, and then your OH continues to be here. Right, so this is not actually kind of it's not on its own step, it's more of a transition state showing why we get the OR at the more substituted side when we have an acid catalyst. Now, we do not need to stick to the nucleophiles that we've seen. We can change nucleophiles, and that allows us a lot of utility in what we're seeing with the epoxide ring and what's able to open up that epoxide ring. So here let's highlight some different nucleophiles. Here I have cyanide ion, here I have SH, here I have lithium aluminum hydride, here I have a Grignard reagent. So during the course of this reaction, where again, remember this is not planar, right? We have some maybe wedge bonds there or dash, there's an equal amount of both. What we will end up with is your OH on one side and your new nucleophile on the other side. Here, your OH on one side, your new nucleophile on the other side. Running out of space here, so I'm just going to write this one further away. Your OH on one side, your new nucleophile on the other side, where you don't even have to draw in that hydrogen with respect to skeletal notation. I'm just drawing it in so you remember that LAH adds hydrogen. And then our final one, the Grignard reagent, OH on one side, and then your Grignard, and I'm going to abbreviate the ethyl group for ET instead of drawing it the other way. I'll show you what the other drawing would look like. If you wanted to show an ethyl here, you would draw it like this. A lot of students don't like it. They think it looks dumb because this is carbon 1 and this is carbon 2. If that's too difficult to see, we can just go ahead and write ET here for ethyl. And of course, all of these would also form the enantiomer. So to save time, I'm just going to write plus EN, saying that each of these would also demonstrate the formation of the other enantiomer as well. Let's wrap up. In this video, we talked about epoxides and reminded ourselves how to make them. Then we looked at the differences between acid and base catalyzed ring opening, especially with the context of stereochemistry. Then we changed our nucleophiles to see that we can add all kinds of things to the epoxide ring. As long as it is a good nucleophile, it can open up that epoxide ring and you get a variety of different products. Thanks so much for your attention. This is Katoni signing out.